Fable 5 is back, but we're looking at a rapidly closing window right now.
Yeah, a very tight window.
If you're on a paid plan today, you can run Fable 5 up to 50% of your weekly usage limit. But, and this is the crucial part, that specific window closes on July 7th.
And the math just completely changes after that date.
Right.
The system flips over to usage credits.
Yeah.
So suddenly, every single token you process is going to cost significantly more. The sandbox we can play in basically gets very expensive very fast.
Which means we really need to change how we operate. So welcome to this deep dive. Today, we're exploring how you can extract the absolute maximum value out of Fable 5 before that July 7th deadline hits. So we've gone through the documentation, the developer notes and the community breakthroughs to pull out 4 heavy-hitting use cases.
Because we have this incredibly capable engine at our disposal, but we're operating with a strict fuel limit. Our focus today is making sure every drop of that fuel translates into a tangible, massive result for your projects.
But before we get into what you should build, we really have to establish how you build. If we don't fix the workflow first, those specific use cases they won't matter. You'll just burn right through your limits. So the fundamental rule here is that you should never, ever let Fable 5 handle your early planning.
Yeah, it's the most common trap I see. People get access to this cutting-edge model, they open an empty prompt, and they type in a vague, kind of half-baked idea.
Like, build me a website.
Right. They'll say, build me a data visualization dashboard, and then they spend the next 20 prompts just trying to figure out what data they actually want to show.
I'll be honest, I still wrestle with wasting usage on messy prompts myself.
They all do.
I'll sit down, type out a rough idea, and then spend 40 messages arguing with the model about button colors and layout structures. It's a really hard habit to break when the interface feels so conversational.
We fall into that trap because the chat interface literally invites casual conversation.
Yeah.
But casual conversation with Fable 5 is just a massive waste of resources.
Yeah.
Loose back and forth workflows are going to drain that 50% limit before you write your first real line of functional code. So the strategy is to use a lighter, faster model first, something like Opus 4.8.
Right, you use that model to dig into the core problem.
Exactly. You shape your prompt, and you verify your technical plan with the lighter model.
You do the messy thinking elsewhere, and you bring the actual building to Fable. I kind of think of Opus 4.8 like an architect with a pencil and an eraser.
I like that.
Erasing a bad line on a blueprint costs you absolutely nothing. You can redraw it 100 times. Fable 5, on the other hand, is the heavy construction crew pouring the concrete. If you make them pour the concrete just to see how it looks and then tell them to tear it down because you changed your mind, you've blown your entire budget.
That analogy holds up technically, too. It really comes down to token economics and how these models process intent. A massive model like Fable 5 is architected to execute complex, multi-step logic across huge context windows. So when you use it for casual brainstorming, you're essentially firing up a supercomputer to do napkin math. It generates far too many internal tokens exploring dead ends.
Yeah, that makes sense.
A lighter model like Opus 4.8 is optimized for faster conversational pivots. It's just computationally cheaper.
But wait, so why exactly is a seemingly smarter, more powerful model actually worse for that initial brainstorming phase?
Because it overthinks the simple stuff. It tries to build deep, logical structures around your vague thoughts, which consumes massive amounts of compute. You want to save that heavy processing power exclusively for the final execution phase.
So think with Opus, build with Fable to save your limits.
That's the baseline workflow. And it really applies to everything we're covering today.
With that rule established, let's look at our first major target. Use case number 1, cloning software you currently pay a monthly subscription for and replacing it with a local private version that perfectly fits your workflow.
We're seeing the true scale of the model's context window here. We have 3 escalating examples that demonstrate what happens when you point this execution engine at complex software. The first is a project called OnGuy's Fable 5 MC.
Which is a fully functional Minecraft clone running directly in a web browser.
Yeah, built using 3.js, which, for those who haven't used it, is just a JavaScript library for rendering 3D graphics in a web browser.
Right.
But the wild part isn't just that it runs in the browser. It's that Fable 5 built almost the entire thing autonomously.
Wow.
It handled the procedural world generation, the block physics, the lighting engine, and the user interface.
It proves Fable 5 can hold all those interacting systems in its context window simultaneously without losing the plot. But, I mean, cloning a video game, as impressive as that is, relies heavily on visual output. Moving to business software raises the difficulty level significantly, doesn't it?
Oh, absolutely. Business software is mostly an iceberg of invisible logic, which brings us to the second example, building a clone of linear.
Yeah. Linear is an incredibly popular, dense issue tracking tool for developers.
Exactly. And the strategy Fable used here took a tutorial route, walking through the build, step by step.
And it handled the complex database states. I mean, it managed the asynchronous data syncing, the user permission layers, the relational databases, linking tasks to projects to users.
Yeah, it wasn't just copying the slick dark mode interface.
Right. It was building the invisible machinery that makes a tool like Linear actually reliable.
Exactly.
But then the challenge shifts again with our third example. What happens if the software you're trying to clone is an AI application itself?
This is where it gets really fascinating. Riley Brown used Fable 5 to clone a tool called Lovable. And Lovable is an AI-driven app builder.
Okay.
So to clone it, Fable 5 had to build a system that makes dynamic, generative decisions. It's not copying static, hard-coded rules like a traditional database.
Wait, I have to push back there?
Sure.
If I'm using Lovable, its underlying AI prompts and decision-making logic live securely on a back-end server somewhere. Fable can't see that source code.
Right.
So how can it possibly clone an AI's abstract thought process if all it has access to is the front-end user interface?
It does it through behavioral reverse engineering. Fable looks at the inputs, the outputs of the application.
Okay, so it watches what happens.
Basically, yeah. It sees what you type into the Lovable interface, and it analyzes the code that Lovable spits out. And from that input-output mapping, Fable infers the hidden prompt architecture on the back end.
That is wild.
It essentially deduces the cognitive pathways and rule engines the original developers must have used to get those specific results.
It copies how an app actually thinks, not just how it looks.
Yeah, and that cognitive mapping is what ties all three of these examples together. Whether it's the physics of a voxel game, the relational database of an issue tracker, or the prompt architecture of an AI builder.
Well, we've just seen how Fable can reverse engineer external software like Lovable. But if it's that good at spotting hidden patterns in other people's systems, it raises an interesting question. What would it find if it looked at our systems?
And this is use case number 2, and it's incredibly practical. We're turning the mirror inward to diagnose our own workflow blind spots.
Okay.
Because if you use AI coding assistants like Claude Code regularly, you're almost certainly repeating inefficient patterns without realizing it.
So we don't ask Fable to build a new app here. We ask it to review how we've been working.
Exactly. You point it toward your recent AI coding sessions, specifically looking in your .claude/projects folder, which is just a hidden directory on your machine that stores your chat history and project context.
Or you can manually feed it your exported JSON transcript files.
Yep. You're giving it the raw logs of every request, every error, and every things you've made over the last week.
But the prompting strategy here is vital. You can't just drop a massive JSON file and say, tell me what I'm doing wrong.
No, definitely not.
You have to instruct Fable to first verify whether those session transcripts actually exist in the directory.
Because if you skip that verification step, large language models tend to hallucinate. They'll start reviewing code that isn't even there. Or they'll just invent problems for you to solve.
So you set a hard constraint.
Right. You say, look for these specific file paths first. And if it finds them, you instruct it to deploy subagents.
How do those subagents actually work in this context?
The main model spins up smaller parallel analytical tasks. So one subagent might scan your JSON logs, specifically looking for retry loops. Moments where you ask for a fix, the code crashed, you pasted the error, and it crashed again.
Oh, I hate when that happens.
We all do. Another subagent might look purely for permission errors or manual file edits you keep making. They parse the data looking for friction.
And if the transcripts aren't available, the prompt strictly forbids Fable from giving a generic, helpful-sounding answer.
Exactly. It's programmed to stop, explain exactly how to export the files, define the required JSON format, and tell you what your next prompt should be. It stays on a very tight leash.
Once it actually diagnoses the friction, you run a secondary sorting prompt. You force Fable to categorize its findings into 4 distinct buckets.
Bucket 1, new custom skills you should program. Bucket 2, manual workflows you need to automate. Bucket 3, small, immediate code-based fixes. And bucket 4, noise, or items that require absolutely no action.
It has to justify why each finding goes into a specific bucket. But what's the actual psychological benefit of having the AI categorize these mistakes this way, instead of just handing us a comprehensive list of all our errors?
It entirely removes the cognitive load of triage. I mean, if I hand you a messy text file with 60 small mistakes you made this week, you're going to feel defensive or overwhelmed.
Yeah, I'd probably just close the document.
Right. But by forcing the model to sort them, it separates the actionable, high-value automations from the irrelevant noise. It transforms a list of failures into a frictionless roadmap for improvement.
We use it to automate our own repetitive blind spots easily.
You stop wasting daily energy on friction you didn't even realize was slowing you down.
Now, let's take a quick second to thank the folks who helped make this deep dive possible.
We'll be right back.
And we're back. So, moving from analyzing our personal workflow logs to analyzing our actual product. Use case number 3 scales this diagnostic power up.
Way up.
If Fable 5 is that effective at parsing JSON transcripts for human errors, how does it handle reviewing an entire complex ecosystem of living code?
Beautifully, because a code base can compile perfectly, run smoothly on your local machine, and still hide deep systemic architectural flaws.
The problem with typical AI debugging is that single files hide the real bugs.
Yeah.
If you only paste one isolated component file into a prompt, the AI lacks the broader context to see how it interacts with the database.
So this use case focuses on macro code review. You hand Fable 5 the entire repository. But again, the prompting mechanics are everything here.
You start with that same verification constraint we talked about. Fable must confirm the real source files exist in the project directory before it writes a single line of feedback.
Verify before acting.
Exactly. Once it confirms the files are there, you instruct it to use those parallel reviewers again.
You deploy the agents to scan the whole architecture simultaneously. Then the main model merges all the duplicate findings, strips out the noise, and ranks the remaining bugs by severity.
It's not scanning for missing semicolons or formatting preferences.
No, it's pointing to specific paths. It highlights a critical flaw in source/lib/filters.ts and explains how it breaks the logic in source/roots/tasks.ts.
It prioritizes core logic failures over minor UI cleanup. But how does Fable actually manage to hold the context of an entire sprawling project well enough to spot a bug that cascades across 3 totally separate files?
It builds an internal abstract syntax tree of your data flow.
Interesting.
Because of its reasoning capabilities, it doesn't just read text, it maps the dependencies. It understands that if a data type exported in file A is improperly modified in file B, it's going to crash the server route in file C.
It tracks the logical thread across directory boundaries.
Exactly.
It finds the hidden bugs between the isolated individual files.
You get a prioritized architectural audit with exact file paths, rather than a generalized list of best practices.
Which brings us to our 4th and final use case, the heaviest lift of them all.
Oh, yeah.
We've cloned existing apps, we've reviewed our personal workflows, and we've audited complex code bases. Now we're looking at building massive custom software completely from scratch.
And this is the exact scenario Anthropic engineered this model for. They designed Fable 5 specifically for highly ambitious coding projects and complex multi-day autonomous implementations.
The primary example here is a repository called the Brafolk Fable 5 World Demo. It's a browser-based procedural 3D open world. The repository notes claim it was built 99% autonomously by Fable 5. The human steering was minimal.
99% is just a staggering number for a project of that complexity.
Truly.
But the secret to that autonomy isn't just the raw power of the model, it's the preparation. This didn't start with a user typing, make a cool 3D world.
It started with a document called project_v2.asmd. It started with a comprehensive PRD. Let's define that term really quick for anyone unfamiliar. A PRD is a detailed blueprint of exactly what to build.
Perfect definition. And this specific blueprint was remarkably rigorous. It defined the visual targets for a 4x4 kilometer open world.
Huge.
It set strict technical constraints regarding memory usage. It established performance floors to ensure a minimum frame rate. It laid out a verification battery, which is a series of tests the AI had to run its own code against before proceeding.
Wow.
And most importantly, it listed banned outcomes.
I have to pause for a second. The sheer scale of this is wild to me. Whoa, imagine an AI generating a 4x4 kilometer procedural universe, complete with rendering pipelines and memory management, completely autonomously just by reading a well-structured text file.
It's incredible.
It really is. But let me ask you about those banned outcomes. Why is explicitly listing what the AI should not do just as critical as telling it what to build?
Well, It comes down to how language models search for solutions. We call these negative constraints. When you give a powerful model a massive search space, like building an entire physics engine from scratch, it will naturally explore weird, mathematically inefficient tangents.
Right.
It might try to invent a new way to render shadows that completely tanks the frame rate.
It hallucinates complexity.
Exactly.
Right.
By listing banned outcomes in the PRD, like do not write a custom physics engine, use this specific established library, or do not use generic gray placeholder textures, you build fences.
You aggressively prune the search space.
You close off the dead ends before the AI even approaches them, which forces all of its computational power toward the correct, efficient solution.
Strict boundaries keep the AI from going completely off the rails.
A vague prompt forces a powerful model to guess your intentions. A specific, highly constrained PRD gives it the exact boundaries it needs to maintain focus across a multi-day coding session.
So if we pull back and synthesize all 4 of these use cases, we have the reverse-engineered clones, the JSON workflow mirror, the macro dependency code review, and the massive custom builds driven by negative constraints. It's time to pull this together into a grand unified theory of Fable 5.
The unified theory is a paradigm shift. Fable 5 is not a standard conversational chatbot.
Not at all.
If you treat it like one, you will fail and you will run out of credits. The workflow pattern that successful developers are repeating is treating this AI strictly as an execution engine.
You decouple the thinking from the building.
You prepare the inputs methodically. You use the cheaper Opus 4.8 model to plan and debate.
Right.
You hand Fable 5 a crystal clear goal backed by strict PRD. You provide it with verified, real-world files and transcripts. And then you just let it execute the heavy lifting.
Success with these models is no longer dictated by the raw power of the neural network. It's dictated by the quality of your preparation. If you throw messy conversational prompts at Fable 5, you'll hit your usage cap by Tuesday and have a half-broken prototype to show for it.
Which nobody wants.
No. We want you to pick just one of these 4 use cases and try it out this week. Test the limits of the model before that July 7th window closes and the sandbox gets expensive.
It's a really unique moment to experiment with industrial-grade AI compute on a consumer plan.
It really changes how you approach problem solving, which leaves me with the thought I've been turning over in my head all week.
Oh, yeah.
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 If models like Fable 5 can perfectly execute these highly complex, multi-day PRDs completely autonomously, if they can build the physics, manage the database states, and write the back-end logic flawlessly just from a set of constraints, the bottleneck of software development is no longer the coding itself.
The execution is a solved problem.
Exactly. Which means the new bottleneck is entirely human imagination. If an AI can build literally anything you ask it to, flawlessly and instantly, how do you figure out what's actually worth building?